Okay, so let's start. So today we are going to learn about combinatorial testing and when to stop testing. So this is today's outline, which is very clear. We have two topics to cover today. So first, let's learn about combinatorial testing. And from the name of this combinatorial testing technique, we can see that there's a keyword, combination, right? And we have encountered some kind of combinations before while along the journey of learning this course. Like for example, we can combine different input values to form test cases. Let's assume we are trying to test this find max function here. So we can see that this find max function will just return the largest integer from the three integers, right? And it is done by comparing the first two integers and then compare the larger one with the third. So we can see that there are relationships among these integers, right? Among these parameters. So there are relationships among A and B, and there's a relation between like C and the larger value of A and B, right? So we can try out different combinations, these four combinations here, to try to cover all the relationships among these input parameters. Like for example, test case A covers the case where A is larger than B and C is larger than the larger value of A and B. And test case 2 can cover the case where A is still larger than B, but C is smaller than the larger value of A and B, right? So we can try to create different combinations of input parameters to cover the different relationships among these input values. And inputs may not only take the form of like function inputs for software testing. For example, sometimes we may do some GUI testing, we may test some forms, right? So different combinations of the values inside the form can also create some interesting interactions inside the software functions, right? So that's why combinations can bring diversity and can cover some cases where the software developer may not have thought about, right? So this is like combinations for input parameters. And there could be other forms of combinations as well. So let's see this one. So this is actually a registry of a Windows application. So, and you can see here, there are some system configurations as well. So because software, they are not just running with user inputs, they are running inside some environment, right? And inside that environment, there could be some configurations, there could be some environment variables. So we can also try out different combinations of configuration options, which may also affect the behaviors of the software we are testing, right? So these are the two sources for us to think about combinations when we are testing the software. And the thing here is because we have different sources for combinations, and we have so many different types of combinations, right? How can we systematically generate different combinations to trigger the different behaviors of the software we are testing? So this is the open question here. And by doing this systematic testing of different combinations of input parameters and configuration options, we are actually doing combinatorial testing. And here is the definition of this. So combination testing, combinatorial testing is a technique that checks all the cases or just some of the combinations of the system level of inputs. And the system inputs could be the user inputs, could also be configuration options, right? And the most common application here are just the two cases we just mentioned. We can try out different user inputs, we can try out different system options. And actually, this is a typical test suite of combinatorial testing. You can see that we are testing different configuration options here, right? We are testing the selection of different operating systems. We can test different browsers, protocols, CPUs, or DBMS. And you can see that this actually, you can see IE inside the browser. So you know that this screenshot is very old. Actually, because IE is outdated, right? So it's actually from the NIST report, which is NIST is actually the National Institute of Standards and Technology from the US government, and it has created some very good techniques. And this report was written about 20 years ago. So they did a systematic study of how can we systematically test different system configuration options and different combinations of system inputs. So this is like a brief introduction of combinatorial testing. And now let's do a live poll to warm up today. So according to the definition of combinatorial testing, what's the color of box here? So we have learned black box testing in week 2, right? And we just learned white box testing in the last week. And we can see that combinatorial testing is about testing different combinations of user inputs or system configurations. So what is, according to this definition here, what is the color of box? So let's do a live poll here. So you have 3 choices. You have black, you have white, you have other colors. So we have learned black and white, but what is other? We will learn about the other color later on. So let's see the results. Okay, many of you chose other. So the correct answer is actually black, because you can see from the definition, we only care about the combinations of inputs, right? Whether it is a user input or a system level of input. So we don't care about what's happening. Like we don't have access to the source code. We don't need to have access to the source code of the target, right? So it's definitely a black box testing technique according to the definition, because we only care about the inputs. So let's continue. And talking about the colors, the other color we are going to learn is gray. So it's in between black and white. It's gray. So it's not a random color like red, pink, or whatever, like green. So it's gray. The other color is gray. We will learn about that in the following lectures. And just now, we quickly went through the definition from the NIST. So we can see that combinatorial testing is also called T-way testing here by NIST. So what is the T-way about, right? What is this term about? Just now we mentioned this T-way testing, right? So what is T-way? So key here is that because a system can have many inputs, right? And we can have many, like, as many combinations as we can get by combining all the inputs. However, we somehow need to limit the number of combinations here, and like different parameters can interact with each other, and we have to specify the interaction level here. And the number t is used for describing this interaction level among the input values. So you may think that, okay, this definition is very abstract. Let's try to look at some concrete examples later to learn better about what is the T-way combination is about, okay? So so as you can see here, T is a variable used for specifying the level of interactions, right? So we can assign different values to T. If T takes the value of 2, then we are doing pairwise testing, which means that we only care about the different combinations of 2 variables. So we don't care about the patterns or the permutations of values made up of 3 or more input values, right? Input parameters. So if we do a two-way testing, we just care about all the possible patterns that could be covered by taking different values for 2 input parameters. And you can imagine if we do 3-way testing, it means that we care about all the permutations and all the possible combinations of 3 or more input parameters, right? And for 4-way testing, it's like we care about combinations of different inputs from 4 different input parameters, right? And so on. So this is this is the definition of T-way combinations. So here, as you can imagine, if we try to combine, we're talking about permutations. The immediate idea you are thinking is like, it's like there could be a large amount of patterns, right? We will be creating a lot of test cases, and let's think about this problem of combination explosion. So we have encountered another type of explosion last week. Can you still remember that? So combination explosion is like if we say something is an explosion, then it means that we are generating a lot of different cases, right? And these cases are because they are generated because we are trying to combine different things, right? And we are trying to calculate permutations of things, right? And in our last week, we learned about actually path explosion. So path explosion is caused by branches and loops, right? So because we are trying to combine different branches to form different paths, right? We are trying to combine different selections or different decision points taken after the loop statements or if statements to combine them together to form different paths. So with that combination, we are getting path explosion. And by combining different values of different input parameters, we also face the problem of explosion here. So let's think about this case. So let's assume that we have n parameters in total, and we are trying to build all the two-way combinations of pairs. So what is the total number of combinations we can get? It is like we are taking 2 items from n items at a time. Like how many different patterns can we have in this case? It's a math problem, right? It's Cn2, right? It's Cn2. And Cn2 is calculated like this. It's n factorial divided by 2 factorial times n minus 2 factorial. So actually this value grows like this. If you plot the value of n here as the x-axis and you use the final value as y-axis here, then the plot looks like this. So the number of combinations actually grows exponentially as we have a larger number of n here. So we may have too many, even if like t, the minimum value of t is 2, like, because if we do one-way combination, then we are not testing any like relations between inputs, right? Because one-way means that we just care about all of the possible values for one parameter at a time. We don't care about the permutations of two values, right? So even if we take the minimum value of 2 here, then we still have this many pairs. Not to say if we have more values, we may take the value will grow upper and upper, right? So we may need to limit the value of t to a certain level, to somehow mitigate the past exposure problem, right? So if t takes a larger value, we may have a larger number of combinations. So how to determine the value of t is a practical problem we are facing. So rather than like testing all the possible values we can have in practice, we normally use a specific value of t. And thankfully, from the experiments that has done by an ISP, we have some suggested values here. So you don't need to talk about, you don't need to go through all the text in detail. So you just need to see this figure here. So the x-axis is the level of interactions. So which means that it's a value of t here. And the y-axis is the number of, is the percentage of the test cases of faults that could be discovered. So we can see that after the value of t is larger than or equal to 2, the number of bug exposure is not growing that fast, right? It's kind of like very flat here afterwards. So the conclusion drawn from NXT is that most of the bugs failures are caused by just one parameter or the interaction between two parameters. So which means that most of the bugs are caused like without the interaction of multiple input parameters. And if we care about the interactions between parameters, we only need to care about like 2 parameters. So the most practical value for t here is normally 2. So normally we just care about pairwise combinations. And then you may think, okay, so now we know that we can try to combine different values, input parameters, and different values of these input parameters to do the testing here. But how do we actually generate the test suite? So do we just exhaustively generate test cases for all combinations? Do we need to have like exactly one test case per combination? Do we need to do that? The answer is actually no. Instead, we can use a technique called covering array. So this covering array can help us to achieve certain interaction level with a minimum test suite, with a minimum number of test cases in the test suite. And let's see how it works later. And so it is actually, like I said, It's just to find out the minimum test cases that can cover all the T-way combinations. So this is the definition here. And it is actually a matrix. We will see some examples later. So this matrix is n times k matrix. So n here, the rows here are the number of test cases. So each row is a test case in a covering array. And the k here are the columns, right? So each column is actually a particular value of parameter. And each cell inside this covering array or this matrix is a specific value of a parameter. So we can see an example here. So in this example here, this is a covering array. So this is just a header for denoting the test cases. And you can see this is a 4 times 3 matrix, right? So we have 4 test cases, we have 4 rows, so we have 4 test cases, and we have 3 columns, which means that we have 3 parameters, right? And each cell here you can see represents a particular value taken by that input parameter, so which is very straightforward. So, and we can denote this covering array like this. So this is a covering array of 4 test cases where it cares about pairwise coverage. It has 3 parameters and each value can take 2 possible values. So this is the notation, a typical notation for covering array. So we can specify the number of test cases included. We can specify the interaction level. We can specify the possible number of values taken by each parameter. Yeah. So apart from the definitions, let's try to learn this by some more concrete examples. Suppose we have a covering array that cares about, remember T is the T-way combination, right? T means the interaction level. So we care about pairwise combinations. And we have 4 input parameters. And each parameter can take 2 values. Yes. So let's say we have parameters are P1 to P4. And we care about 2-way combinations, and each parameter can take 2 values. So let's just assume that the 2 values are 0 and 1. So how many pairs do we have? How many combinations do we have? It's C42, right? It's C42 means it's C42 means it's 4 times 3 times 2 times 1 divided by times 2 times 1 divided by 2 times 2, right? So the value is 6. So we have 6 pairs in total, right? There are 6 pairs in total. And these are the 6 pairs. So P1, P2, P1, P3, P1, P4, P2, P3. Why not P2, P1? You know, why not? Why don't we have P2, P1 here?
Same as the P1.
Yes, because we don't care about orders, right? In combinations. We just care about the appearance of the parameters. We don't care about their ordering, right? So P2, P1 actually equals to P1, P2 here. So we have P2, P3, P2, P4, and P3, P4. So we have these 6 combinations in total. And we want to cover all the combinations. We want to create test cases to cover all the possible combinations for each pair. And each pair can have 4 different values, right? Because each one of them can take 2 values. So each pair can have 4 different patterns. So if we just generate the test cases exhaustively, how many test cases do we need? 16, right? Because every value can take 0 or 1, so it's 2 to the power of 4, right? It's 16. It's not 4 times 6. It's actually because there will be some duplicates if we do 4 times 6. So the total number is 16. But do we need all the 16 values to cover all the possible combinations for each pair? The answer is no, right? We just learned that is no. So this should be 16. This is an error. This is 16. It's not 26, 24. 24 is 4 times 6. Sorry. So we just learned that, okay, if we exhaustively try out all the possibilities, we can have 16 test cases. But with the covering array, we only need 6 test cases to cover all the possible patterns taken by each pair of input parameters. And let's see why. And this is the final test suite we need for achieving the goal of covering all the possible patterns for each pair. So we have 6 pairs, right? So the first pair is P1, P2. So let's try to cover all the way from 0, 0 to 1, 1, okay? Let's try to find test cases that can cover all the 4 patterns for P1 and P2. So the first one is 0, 0. We can see that the first test case can help us to cover this case, right? And for 0, 1, we can use test case 2, right? And what about 1, 0? Test case 3. What about 1, 1? Test case 4, right? So we can use these 4 test cases to cover the 4 different patterns that could be possibly taken by P1, P2, right? That is pair. And what is the next pair we can have? P1, P3, right? P1, P3. So can we find 4 test cases that can cover all the possible patterns from this covering array? Let's try to find 0, 0. So the first test case can cover 0, 0, right? What about 0, 1? The second one, right? What about 1, 0? Test case 4, right? What about 1, 1? Test case 3, right? So you can see you can use these 4 test cases again to cover the other 4 patterns for P1, P3. And what is the next pattern here? What is the next pair here of input parameters? P1, P4, yes. So can we find 0, 0 from this table, from this covering array? Case 1, right? And what about 0, 1? Case 2, 1, 1, 1, 0. Case 4, case 3, sorry. What about 1, 1? Case 4, yes. So you can see that these 4 test cases can already cover many patterns, right? So what is the next pattern? We have 6 in total, right? What is the next pattern here? P2, P3, yes. So can we find the 0, 0 for P2, P3? Test case 1, right? Can we find 0, 1? Which test case is 0, 1 for P2, P3? Case 3, yes. What about 1, 0? Case 4. Case 4. What about 1, 1? Case 4, right? You can see that these 4 test cases can already cover 4 different patterns, 4 different pairs, and all the patterns for 4 different pairs. And what is the next pair we can have? P2, P4, yes. So can we find the 0, 0 for P2, P4? Is 1. Can we find 0, 1 for P2, P4? Can we find it from these 4 test cases? No, right? We have to find it here, right? So 0, 1 for P2, P4. What about 1, 0? We cannot find it from the previous 4 test cases, right? So we have to create another test case here. And 1, 1, we can find it from the second test case. And what is the last pair we can have, last combination we can have? P3, P4, yes. So can we find 0, 0? P3, P4? Yes. And 0, 1? 0, P4? This test case 4, right? And what about 1, 0? This one. And 1, 1, test case 2. So you can see that the first 4 test cases can already cover like all the possible combinations of values of 5 different pairs, right? We only need 2 more test cases for this pair here. So instead of trying out all the possible combinations or all the values that could be used, we can actually use 6 representative test cases to cover all the potential patterns, pairwise patterns we can have, right? So this is why we need to calculate this covering array. So it can help us to reduce the size of the test suite we have. So this is the covering array. So now let's go back to, so now we can see that it is actually very useful, right? So it can help us to, so instead of generating all the possible combinations, we can be very efficient. We can try to just use some representative values. And it can have a guarantee of the coverage, right? Because we can systematically cover all the potential patterns, right? And it is very scalable because instead of like finding out all the exponentially growing number of combinations, we can select representative values. So this is the advantage of using covering array. So now we wonder, okay, we know that covering array is good. It can help us to, it can provide a guarantee of coverage for different patterns, right? And it can help us to reduce the size of the test suite, right? So how do we calculate this covering array? So how do we know that we need that 6 particular test cases, right? So there are some algorithms for calculating this covering array. However, it is not easy. So there are some meta-heuristic algorithms which are simulated annealing and kinetic algorithms. And there are some other algorithms like heuristics based, which is known as greedy algorithms. So let's try to learn the simpler ones here, the greedy algorithm here. So greedy is good. So let's go through the greedy algorithm step by step. So you might have learned greedy algorithm somewhere else, right? So greedy algorithm is like to maximize the gain at each step, right? So the key here is how do we measure the gain of value here at each step. So the gain of value here is that at each step we try to create the test case that can maximize the number of patterns we can cover at each step. So this is the key of greedy algorithm here. So let's try to do it with an example. Let's still use the same setup, but instead of using like P1, P2, P4, we use ABCD for the 4 parameters here. And let's still try to do the 2-way combination. And let's still assume that each parameter can take either 0 or 1, okay? So step 1, so the initial test case. we can just use a random test case. So let's assume that we are starting from 0, 0, 0, 0. So this is the covering array we have right now with the initial seed. So you can see that all the values are, all the parameters here are taking the value of 0, right? So this is not the covering array. This is something like help us to take note of what has been covered. So this is just like a scratch pad. Okay, so we can see that on this scratch pad we have like 6 different combinations, right? We know that there are 6 different combinations, which is C4, 2. And why do we have 4 columns here? What are the 4 columns representing? Each column is representing a different pattern, right? For each pair, right? Because we have 4 different patterns per pair, right? So we have 0, 0, 0, 1, 1, 0, and 1, 1. So that's why we put 4 columns here. So let's continue. So let's try to grow this. Let's try to grow this covering array by finding the next test case greedily. Okay. So the next step is, can we come up with a test case that can introduce 6 new pairs? And the quick answer is yes. And let's see why. So, I think I spoiled the combination, the animation here. But anyway, so just now we covered all the test cases of 0, 0s, right? So can we still allow A to take the value of 0? Did we try out all the potential pairs where A is taking the value of 0? No, right? Because A is like, we haven't tried out, for example, we haven't tried out 0, 1 for A, maybe, right? So A can still take the value of 0, right? So let's assume that since we haven't covered all the cases where, all the patterns where A takes the value of 0, let's try to use 0, put a 0 here. So should we allow B to take 0 or 1 here? You know the answer is 1, but why don't we allow B to be 0 again? Why? Yes, because we are greedy here. We are greedy. We already have the case where AB is 0, 0, right? So we shouldn't allow B to be 0 again, right? So that's why we need to take the value of 1 for B here. What about C? Shall we take the value of 1, 0? Because 0, 0 has already been taken, right? So it's better to put C as 1 here. And the same goes for D, right? So we should put 1 here for D, right? And this actually automatically gives us 6 new pairs. You can see that we have tried out all the, because except for A, all the other values are 1, right? So for all the other patterns that are not involving A, they are just all 1, 1, right? And for all the values involving A, they are just 0, 1, right? So this is the second step. And this is what we have on the scratch pad right now. And let's try to see if we can create another test case that can produce 6 new pairs. And this time, unfortunately, the answer is no. And let's see why. So let's first decide the value of A here. So can we still take 0 for A? Can we still take 0 for A? Yes or no? You can see that we have tried out 0, 0, all the 0, 0, and 0, 1s for A, right? Because we just need, if you care about A, we just need to pay attention to the first 3 rows. So we can see that all the possibilities of 0, 0, and 0, 1 for A has been taken, right? So we have to use 1 for A, right? Can we use 0 for B? It's yes, right? Because 1, 0 hasn't been taken, right? So we can take 0 for B. What about C? Can we take 0 for C? Sorry. Can we take 0 for C? I just accidentally clicked the animation because there are so many animations in these slides. So we better not take 0 for C here. Why? Because you see, you may wonder, okay, 1, 0, like for AC is not taken, right? Why can't we give C a value of 0, right? The reason is that we also need to care about B since we have settled the value of B here, right? So we have to think about the combination of B and C, right? So if we take the value of 0 for C, then we already have 0, 0 for BC, right? But we don't have 0, 1 for BC. So taking the value of 1 for B and for C here can maximize the gain, right? Because we are getting 2 more patterns out of by selecting the value of C to be 1, right? So this is greedy algorithm. And let's think about the value of D. Can we make it 1 or can we make it a 0? We need to think, right? We need to think, okay, if we take the value of 0, then for AD, we can have 1, 0, which is new. If we take the value of 0, then BD is not new, right? And CD is also new, right? But if we take, so we can have 2 more patterns. If we take the value of 1 here, then AD is 1, 1. BD is 0, 1, which is new, but CD is not new. So in this case, it's a tie, so we can take either 0 or 1 here. Let's assume that we just take the value of 0 here. So we can, so no matter 0 or 1 we take, we will eventually have a duplicate, right? So we don't care about whether it's 0 or 1 here. So let's assume that we take the value of 0 this time. And this is the covering map we are going to have after including the third test case. So let's continue. So just now we have covered all the cases of like AB to be 0, 0, 0, 1, 1, 0. Now we just care about AB to be 1, 1, right? And the same goes for the decision of C and D. So every time we just compare, like if we take the value of 0 or 1 for each parameter here, how many new patterns can we have? And we select the value for that input that can bring us more new patterns that can be covered. So in this case, the decision here is 0, 1. So we don't go through the details because it's quite repetitive here. So it's 0, 0, and 0, 1. So now you can see that we have 2 more cases left, right? So we need to deal with BD. So in this case, so in this example here, B and D, we need to have 0, 1, and 1, 0 for BD, right? So we just append 2 more test cases where B and D can take 0, 1, and 1, 0, and we don't need to care about the rest of the values for A and C. And then we can get this. So this is how we build the covering array using the greedy algorithm. And you can see that this is exactly the covering array we just used for demonstrating the advantage of using this covering array, right? So just now we learned that, okay, using using greedy algorithm, we can build the covering array step by step, and you may have encountered the greedy algorithm in some other like situations or solving other problems, right? So the problem of using greedy, the advantage of using greedy algorithm is very straightforward. So it's very fast, it's very practical because it's very easy, right? And it can produce the near optimal test suite very quickly. But you can see a potential cons here, right? Potential disadvantage here. So it's near optimal. Like many other applications of greedy algorithms, we may not be able to get the best solution. So if we apply greedy algorithm, most of the time we are getting the near optimal solution. So the limitation here is because for each step, we don't look ahead, right? We are just greedy. We just see how many new patterns can each value give us, right? So we don't look ahead. So we are not searching for the global optimal. We are looking for local optimal. So in this case, we may not be able to produce the smallest possible test suite we can get for that covering array. So we may not be able to get the smallest covering array we want. And therefore for higher, if we for pairwise combinations, normally greedy works well, like what we have demonstrated. It can give us the best solution in that case. But if we have a higher value for t, because of the search space, because the search space is much larger, right? So we may not be able to get the best solution, and some meta-heuristic algorithms may get smaller test suites in this case. But we will not learn them here, and we will learn genetic algorithm for test-based generation in some later lectures. So just now we consider we have learned like the definition of combinatorial testing, and we have learned how do we calculate the covering array to create a smaller test suite, right? And we know that, okay, combinatorial testing has the advantage of being able to systematically cover the different interaction levels for input parameters without you exhaustively trying out all the possible combinations, right? So we can use some representative values by constructing the covering array. So that's the advantage. But what are the limitations of combinatorial testing? So we have encountered one first. So there could be combination explosion problem. And this combination explosion problem, even if we just discussed that we can limit the value of p to be a smaller value to somehow mitigate the problem of combination explosion. But we just limit the number of interactions, right? We just limit the number of input values we take from all the input values. But what if the number of n is large? So what if the number of total input parameters is large? Even if we just do a pairwise combination with a large n, we can still have the problem of explosion, right? So this is known as parameter explosion. And we may also have the problem of constraints. So in some cases, not all the combinations of different input values are meaningful. Like for example, let's assume that we have two input fields, month and date. For February, if we put the date to be 30, then this combination is not a valid combination, right? So not all the combinations between different input values are meaningful. So in this case, if we just create the test case without considering the constraints, we are creating a lot of invalid test cases. So which may not be able to help us to cover some program behaviors. And if another limitation here is that it's kind of related to the constraints, because there could be many, because this is a black box technique. We don't care about what's happening inside the program. We don't care about the dependencies like constraints. Some of the dependencies are actually captured by some of the constraints are actually captured by the dependencies among the input parameters. Because we don't care about this, so we may not be able to trigger some interesting behaviors inside very complex software. And this is another limitation of combinatorial testing. Okay, so before we cover the next topic, let's have a 10 minutes break, and I'll see you at 5:06. Yes, yeah. Very good. Here, okay. So it has a gravity speaker. Just gravity to cover like all the patterns with the gravity and it can be very efficient. It's unscalable just because of action.
If you compare with the entire permutation, of for Hilbert's combination of primitive. Why there's still maybe because because even if we just use pairwise, if we have large number of parameters, and maybe a large number of different values that each one can take, the search space is too large. So even if we try to build a combinatorial, it could be very, very large. Although it's already although we are trying to further representative, there are too many representative values. It's simply because of the size. It does. It's not a disadvantage. It's like a limitation in practical application. It's already dropped a lot. Yeah, it has dropped a lot, but it's still with such large spaces. Yeah.
Okay, so let's continue the second half of this lecture, which is when to stop testing. So we have learned many testings so far. We have learned functional testing, right? Black box testing. We have learned non-functional testings. And we just learned combinatorial testing. And we will learn some gray box. Just now we learned there's some other colors, right? We will learn gray box testing later. And we will learn different levels of testing later. And we will learn different testing oracles. And we will also learn mutation testing, which is testing of testing. So have learned so many testings so far. And you can see that it's all about testing in course. But when to stop testing? So is it yet another new kind of testing called to stop? It's actually literally when should we stop doing testing? And you may wonder, okay, maybe after this term you can stop testing because you are fed up with all the testings. So actually in practice, in industry, we need some criteria to stop testing. We need to have some quantified metrics for us to decide when to stop testing. So let's learn about this. So these quantified metrics are known as stopping criteria. And you can think of this problem from different aspects. So you can see all these aspects are actually related to software, right? So if we think from the requirements aspect, what we can do is we can write the tests based on the requirements and stop when all the tests can pass, right? And if we consider the actual code, like the implementation of the requirements, we can try to achieve some structural coverage level, right? We have learned in our last week, we can stop testing when we reach certain level of some structural testing. For example, if we have covered 90% of the statements, we can stop, right? So we can also consider that. And we can also think about the budget we have, right? So maybe we have run out of budget for hiring the testing team, or maybe we are running out of time, then we can stop testing. And we can also try to, similarly, we can try to follow the budget according to the plan, right? So these two are basically the same. And the ideal case is that we can prove, however, you can see all these previous criteria, they have their own limitations. And the ideal case is that we want our software to be dependable. We want to prove to the users that the software is dependable. And this is what we learned from lecture 1, right? We learned dependability from lecture 1. What we want is we want to build dependable software. And we learned the definition of dependability in our very first lecture. Actually, there are 4 different measurements or 4 different sub-criteria related to software dependability. So the first one is correctness. The second one is reliability. And the third one is safety. And the last one is robustness. So can you quickly recall what are all these concepts about? So correctness means, so when we are talking about correct, we have to have some golden standard, right? So what is the golden standard for correctness? Correctness is, the golden standard here is requirement, right? The user requirements. So correct means the program aligns with the specifications or the requirements, right? And reliability means the software works for some period, for the period that we are observing it, right? So it's like, so a more formal definition here is it's a measure of the likelihood of correct behavior for some period of observations, right? So safety means we can avoid some undesired situations, right? And robustness means that the software can gracefully handle the failures, right? So these are the four concepts related to software dependability. And let's see which one is the most practical one for us to decide when to stop testing. Let's go through them one by one. So, because we know that it is impossible to find out the faults, so we have to stop at some time, right? So we have to stop, and let's try to see which concept is more suitable for measuring dependability. So correctness is actually hard to be proven because we have learned in our second lecture that we can use some formal verification techniques to prove a software aligns with the specification, right? But that involves an expert to do the proving manually, right? So it could be hard, very hard to prove the correctness. So let's not use correctness here. And robustness and safety are important, but they're far from enough for measuring dependability because both of them are related to some rare cases or corner cases, right? Because robustness is about handling failures gracefully. And normally, failures are triggered by some corner cases, right? And safety is more obvious because these hazard situations are normally not going to happen like every day, right? So they are important, but they are not representing the majority of the daily use of the software, right? So the last one, we only have one choice left, and that is reliability. So we can actually try to measure, because dependability involves these four properties, and we can use reliability to roughly help us to measure dependability. So this is the case. So now we are converting the problem from like when to stop testing to how do we measure the stopping criteria. And we found that, okay, dependability is good, so how do we measure dependability? And now we are converting the problem into how do we measure reliability, right? So now the problem is how do we measure reliability? So the definition of reliability is if we try to look from the angle of gradient test, the definition could be like this. So reliability is the probability of failure-free operation for a specified time or in a specified environment. So this is like for when we are observing this software, right? And for a given purpose. So the given purpose is like the scenarios or the features we are trying to test, right? So you can see that the purpose actually depends on the user, right? And the specified environment actually depends on the system for running the software. And informally, reliability could be described as a measurement of how well the user think the software runs. So it's like how good is about the feeling of the users. Right? So, so reliability is like improved when the faults are removed. And because it is actually related to the feeling of the users. So if we so the removal of faults may not lead to the exact amount of improvement in user feeling, because users may not, because a software could be very buggy in some rarely used features, and the users cannot feel that, like they are not, because they are not using those features, so they don't feel that this software is very buggy or very bad. But if the bugs are inside somewhere where the users are frequently using them, then the feeling is very bad, right? So removal of the bugs doesn't always, like improve the user experience. So that's about the definition and some interesting properties of reliability. And we just define that reliability, and we need to somehow measure reliability and in some quantitative way, right? So let's learn about some measurements for reliability. The first one is probability of failure on demand. So even the abbreviation is very long here for this one. So it is actually used to measure the probability that a service request will fail over a period. So the calculation is very easy. So it's just it's a probability. So it's calculated as the number of failures divided by the number of total requests in a period of time. So this is the calculation of this. So if we have a overload of 0.001, it means that 1 out of the 1,000 requests failed during the period of observation. So this is the definition. So the application of this measurement should be used in situations where a failure request is serious. And the characteristic of this one here is that it is independent of the frequency of requests, right? It's only about the probability. So imagine over a period of time. So imagine in that period of time we have maybe 10K or 100K requests. We don't care about the frequency, right? We don't care about how many failures we have, right? So it doesn't care about the frequency, it just care about the probability of having a failure. So that's the case. And the second measurement we can use is availability. So the availability reflects the ability to deliver the service to the users when available. And it is calculated like this. So we use the number of uptime divided by total time. So we should, when determining the value of availability, we should take into consideration the repair and restart time. So the time period when we are repairing or restarting a service, it is considered as not available. And we don't care about the incorrect computations. So it means that the system, the service is available, but it could be buggy or faulty. But we don't care about the bugs or faults. We just care about whether it is accessible by the user or not. So even if it may malfunction, we still count it as available. So this is availability. So we just care about whether it is up or not, right? We just care about whether the service is there or not. So Availability of 0.0999 means that a system is available 99.99% of the time. And 0.9 means if the system is down. So to give you a feeling of like what does the number mean here is, if we have an availability of 0.9, it means that there's roughly 2 hours of downtime every day. And if it is 0.99, it means that there's like 15 minutes of downtime every day. And if it is 0.99, then it's 84 seconds. And if it is 0.999, then it is just 8 seconds per day. So we are not able to use, so if we can achieve the availability of 0.999, it means that we are not able to use the system like for 8 seconds per day, which is already a very good value. And the third measurement we are going to learn is the rate of occurrence of fault. So actually all the measurements, they are telling us how they are calculated by their name, right? So this one is all about the rate. Just now, when we are talking about fold, we don't care. We only care about the probability. We don't care about the frequency, right? For this one here, we care about the rate. So this one here, we just use it to measure the probable number of failures given the period of time, but we don't limit the number of total requests. So if we have this 0.02 value of this measurement, it means that in 100 time units, we are going to have 2 failures. So this one is like related to the frequency. It doesn't care about the number of requests compared to the first measurement we learned. So most of the time, this is the most appropriate metric when like requests are like getting into the service based on a time. So for example, if we are doing some backend service, then this one is probably the most useful one here. And there's another measurement which is calculated based on which is calculated based on the individual failures. And this is also very widely used, which is known as mean time between failures. So this one is to measure the average time between observed failures. So it means that after we observe the failure, how much more time does it take to fail again? So this is the mean time between failure. And this one here actually requires us to log the timestamp of each failure, right, in order to calculate. And mean time of 500 means that the time between 2 failures is 500 time units. So it depends on the time unit, similar to the previous one. So as we can see that we have 4 different measurements for calculating reliability, right? For quantifying reliability. But you can see that every one of them relates to some properties, like some are related to the number of requests, some are related to time units. So we need to log something in our system to calculate these values, right? So these are the types of data we need to log. So for fold, we need to measure the total number of requests in that period. And we also need to measure the number of failures. And for this one here, rate of the failures, so we need to calculate time, right? Because it's about frequency. And for MTBF, we need to care about the timestamps, right? And for availability, we just need to care about the uptime, right? So here's an example of how to calculate everything here. So assume that we provide the software with 10K requests, and we got wrong result on 35 requests, and we have crashes on 5 requests. So what is the code fault here? So because we get wrong answers or like even worse cases like of crashes, so we have 40 errors of failures in total, right? So both wrong behaviors and crashes are failures, right? So we have 40 in total, and we have 10K. We have 40 failures, and we have 10K requests. So it's as simple as 40 divided by 10K. So this is very straightforward. And let's assume that we run this software for 144 hours, which is like 1 week, right? 24 times 7. Oh, no. 24 times, 24 times 6 days. So, and during this period, we have 6 million requests, and the software failed on 6 requests. So what is this rate of occurrence of fault? So it depends on the time unit, right? Rate, you can see from the name, rate is related to frequency, right? So frequency is related to time. So we use 6 divided by 144, right? So that's why it's 6 days. So this is very interesting here. So it's about this, so 0.04 per hour. I need to mention the time here. And for pole fault, it's probability of failure on demand. So when we see the keyword demand, we are talking about number of requests, right? So we don't care about the frequency, we don't care about time, we just care about the number of total requests. So we have 6 million requests, and we have 6 failures. So it's 1 over a million, right? So what about mean time between failure? It's like 144 divided by 6, right? So it's roughly 24 hours between failures. Let's continue. So let's assume that we have a piece of software that has the rate of occurrence of failures of 0.001 failures per hour. So, however, after each failure, it takes 3 hours on average to restart, to repair the system and restart the system. So what is the availability per year? So what we need to do is we need to first calculate how many failures do we have, right? So failures per year, we can calculate it like this. So we have 24 hours per day, and let's assume that we have 365 days, which is not a leap year. So we have roughly this many hours. It's 8,760 hours. And the failures is roughly this, right? 8.76 failures per year. And each failure takes 3 hours to recover. So the downtime, comparing to uptime, the downtime could be calculated by 3 times 8.76, right? So, and we can use the total number of hours per year minus the downtime divided by the total number of a year to calculate the availability, right? So this is how this availability is calculated. So we calculate the downtime first, and then we use the total time minus the downtime to calculate the uptime, and then divide it by the total time is the availability. So the availability is 0.997, roughly this number here. So this is how this availability is calculated. So based on what we have learned, let's try to see a real world case of this measurement of reliability. So this case is about the cloud status. So if you are using cloud code, sometimes it may not work, and you may want to go to this page and see if the service is down or not. So you can see that just yesterday there was like outage, but for 1 hour, and during that period you may not be able to use cloud code. And so in this page, the question is, in this page, what is being measured here on this page? We have learned 4 different measurements, right? What is measured by this page of cloud? It's actually, the keyword is inside this web page. You can see the keyword, right? And it's a pity that they don't allow access to the newest models outside America. But it's not very bad because there are some open source models that can like work like similarly to Fable, to the unavailable ones. So what's the measurement used here? You can see the keyword uptime, right? So let's see the results first. Okay, very good. Most of you have got it correct. I think some of you may just randomly click to get the gen. So, but that's okay. So, yes, the answer is availability. So it's helping us to, it's helping us to see whether the service is available or not. So because of the keyword uptime. And therefore, that's why if your cloud code you are not is complaining about API outage, you will need to check this page to see if it is your network's problem or it is the service problem. Okay, let's continue. So just now we learned, okay, there are 4 different types of measurements we can use to calculate reliability. But how do we use this for testing? So we can measure the reliability now with these measurements, but we are still not answering the problem of when to stop testing, right? So we have to introduce another technique called statistical testing, which can help us to answer the question of when to stop testing. So in this statistical testing, rather than, so for normal testing, we are looking for bugs, we are looking for faults. So rather than looking for faults, in this scenario, we are using test cases to test for reliability of the software. And in order to test the reliability of the software, we should match the usage profile of the users. Like for example, just now we talked about the difference between the removal of faults and improving the user experience, right? Removing bugs doesn't always improve user experience because sometimes we are removing bugs in features that are rarely used, right? So we should create test cases that match the usage profile, right? And we can record errors, failures, and some other data we just discussed to calculate the 4 different types of measurements, right? And then we can determine an acceptance level of, like, for example, a very high number of availability or a very low number of probability of the fault, right? So we can then, if the level, the acceptance level is achieved during the period of observation, then we can stop testing. So this is the idea of statistical testing. So you can see that we already learned the 4 different types of measurements, and we know that this acceptance level is as simple as just setting a limit for these 4 measurements, right? So what about this user profile? So this user profile actually has an official name called operational profile, and it actually reflects how the software is used. And it actually consists of different classes of inputs and the probability of them being used for the software. And it can be specified in advance if we don't have real users. So, but it could be very hard for new systems, right? Because you may not have enough users to use it. So that's why some companies, they have alpha tests, they have beta tests. They try to attract some users to create some operational profiles. And you may think, okay, this operational profile sounds very abstract, but you are encountering it somewhere before, definitely. Maybe you have seen when you install some new software, and you may see this dialog box, right? So it's kind of like asking you whether are you willing to submit your data to our server to improve our users' experience. Actually, they are collecting your usage profile. So if you click yes, but if you click no, so it's not sharing your usage profile. So this is operational profile, and this is a normal procedure of doing statistical testing. So it's kind of like combining everything together into some kind of process. So what we do is we try to form this operational profile first, either by simulating the users or collecting real usage data from users. And then we can construct test inputs that could reflect the profile, because this profile tells us the likelihood of some feature being used by a user, right? So we can construct test inputs according to this probability or likelihood. And then we can try to, now we have the test cases, we can try to apply the test cases and calculate the measurements, right? And then we can, if we can observe some failures, and the failures is the failing level is below what we expect, then we can calculate the reliability, right? So statistical testing can help us to estimate reliability, and sometimes even without actual user, as far as we can get this operational profile properly. So this is the typical procedure of statistical testing. And there are some limitations of this testing technique, like all the other techniques. So the first one is there are some uncertainties about this operational profile. So because users, the actual operational profile may change over time, right? So the user group may change, user behaviors may change. So this operational profile should be kept updated. That's the ideal case. But in most of the time, it could be outdated. So it may change over time. And sometimes we may, because for new systems where we don't have users, we may try to obtain the operational profile from some similar existing systems, right? And in this case, the the profile may not align. So this could also cause us some issues. And the second limitation is we may suffer a very high cost for test input generation. Because in order to observe failures, sometimes we may need to generate a large amount of requests in a short period of time. And in this case, the cost could be very large. And you can imagine for Anthropic, the company that built cloud, for them to test the availability, they need to run the models on GPU servers, right, which is very costly for them to run the test. So you can see that this, just because of the large volume of test cases, the large volume of the requests, it could be very expensive for us to do statistical testing. And the third one is statistical uncertainty. So because we need to observe enough number of failures to calculate a meaningful value for these measurements. If let's say for example, if we observe no failures during maybe 10 hours of observation, so we are getting a zero value for the rate of the observed faults, right? Or maybe the probability of the faults. And in this case, it's hard to, we are very uncertain to tell that the system is free from bugs because we just don't have enough data to estimate the likelihood here. So sometimes we may need to run this test long enough and observe the system period, make the observation period long enough to collect enough data to be more confident. So this is another problem. So this is how it's done. So normally we just set a limit, and after the failure drops, then we can tell that okay, this is acceptable. But if we don't have enough observations, we are not very confident when saying that the software is free from bugs. So that's the limitations. And before we end today's lecture, let's quickly go through what we have learned today. So we covered two major topics today. The first one is combinatorial testing, and the second one is when to stop testing. So for combinatorial testing, it is a black box testing technique, right? Why? Because we don't have access, we don't need access to the source code, right? We don't care about the different combinations of actual values between input parameters, right? And talking about combinations, we can combine multiple input parameters together, right? And we can select different numbers of input parameters to combine them together, right? And that number here is known as, it has a special name, it's T, right? T-way testing. So if we do two-way testing, it means that we are doing a pairwise testing. We are trying to combine two input parameters each time, right? And we care about all the patterns that could be covered by the pairs. And in order to, because there could be so many combinations, in order to avoid the problem of suffering from this large number of potential test cases, what we want is we try to build a covering array, right? This covering array can help us to select representative values that can represent all the potential patterns, right? And in order to calculate this covering array, it is not easy. We have to use some algorithms, and we learned the greedy algorithm for covering this, right? For calculating this covering array. And that's all about combinatorial testing. And then we learned about when to stop testing. So when to stop testing, the story is like this. So we need to have some stopping criteria, right? And the software dependability is like our ultimate goal, right? So we try to derive the stopping criteria from dependability. However, dependability is made up of 4 different properties, and reliability is the most practically useful one to represent dependability. So we are converting the problem into how can we derive stopping criteria by calculating reliability, right? So in order to calculate reliability, we have to have some metrics for measuring or quantifying reliability, and we learned 4 different measurements. So the first one is related to the number of requests failure divided by the total number of requests. The second one is related to uptime divided by total time, which is availability, right? And the third one is related to the frequency, right? It's the number of failures over a period of time. And the last one is like mean time between failures. So like it's how long does it take to see a failure again, right? So we have these 4 measurements. And if we combine these 4 measurements with the actual user profile or the operational profile of the software, we can do statistical testing to try to simulate how the users would experience failures and bugs in real usage, right? So that is statistical testing. And we can use statistical testing to estimate to get the acceptance level by making sure that we can lower the failure rates and have high enough availability, right? So that's when we can stop testing. Okay, so that's all for today's lecture, and thank you for coming. Thank you.
We have an assignment too soon.
Yes, we will release the specifications for assignment to next Monday. And we are actually planning to improve the playground. So you don't need to worry about like the format of the files, the folders, and so on.
Yeah, I was really confused how to
Yeah, we are going to improve that. You can just, we are trying to implement a feature to allow you to like export your answers with 1 click. So you can just export a JSON file and submit to us. So, yeah.